So we've plugged our system into the network and we've gotten an IP address. We've used DHCP to request information from a DHCP server and get IP address and information that we can use to communicate on the network. Now, the first thing we probably want to do is either maybe update the system, browse the internet, go out and download some software, something like that. And to do that, we are going to be communicating with a domain, right? Maybe we want to go to google.com and download Chrome. If we put in google.com, well, let's think about that. We've looked at the IP header, we looked at the TCP header and so on. We know that there's no field, there's no way to communicate with the system using a domain name, right? We need an IP address. That's how we communicate with systems on the network. But often we don't know the IP address. Could you tell me the IP address of google.com right now? Maybe you could, but most people can't. I certainly can't. So how do we figure that out? Well, that's where DNS comes in. DNS, or the domain name system, is a protocol that's used to resolve host names to IP addresses. So just like in that example, we have google.com, and we need to figure out that the address that google.com is 72.125.34.12. So that's the internet example. We have the similar example inside of our own network, right? Your workstation has a DNS name assigned to it. Many of the servers you can communicate with are. Maybe there's a file server you have access to, and you go in and you open up, my computer, and you type / server 1. Well, you don't communicate via the name, you communicate via an IP address. So what's actually happening here is a DNS resolution process wherein server 1 is being translated to 192.168.1.5. So very simply, it's DNS is used to resolve host names to IP addresses. Has a little bit of other functionality as well, but that's really the main core functionality that is DNS. Now, DNS is a critically important protocol. I believe it was Dan Kaminsky who said that the DNS is basically the glue that holds the internet together, and that's probably, I would say, certainly not too much of a stretch. So there's a lot of reasons for that. One is, again, IP addresses are hard to remember. This is especially becoming the case when you consider how IPv6 addresses are formatted, which is darn near impossible. IPv4 addresses, maybe. IPv6, not a chance. So short names, domain names are a lot easier for us to remember, and that's how we think about things when we communicate on the internet. The other thing are DNS names give us a lot more flexibility. Google.com doesn't just have a single IP address that's used to host their web servers. They have lots of them. They're doing a lot of crazy load balancing. But nonetheless, everyone who goes to their site goes to google.com, and they get translated to the appropriate IP address they need to communicate with based on a number of factors, right? So it allows flexibility in terms of scale. Also, consider, let's say we're doing a server migration, and I have chrissanders.org, and it's pointing to a specific IP address. Well, if I'm, migrating to a new server, I can go ahead and set up that entire server, give it a new IP address, and when I want people to switch, all I have to do is change that DNS mapping from chrissanders.org from one IP address to the other. And that way, I'm not having to tell anybody to go to another address, do anything like that. I'm doing this on the back end. It allows for a more seamless migration. So DNS also allows some degree of flexibility in how you manage your network. So it's used in a crutch a little bit in that way, and that makes it very prevalent, very useful. You'll see DNS on virtually every network to be able to resolve host names to IP addresses. So it's very important. It's really the next step along the path of application layer protocols that we want to look at here before we get to HTTP and SMTP. So we're going to touch on some of DNS here, really the core functionality, a little bit of the structure, some function of normal DNS queries and answers. We're going to talk about DNS recursion, and we're going to talk a little bit about a couple types of abnormal DNS that you might run across, like things like fast flux. If you want to read more about DNS, it's really covered in a lot of RFCs. You're probably going to want to start in 1034, but it's defined further in a bunch of different RFCs with differing information on additional functionality of it. But 1034 is probably where you want to start if you want to read further beyond what we cover here. Now, DNS exists as a transactional protocol, and that means not unlike DHCP, right? We had a client and a server that client sends some data, the server responds, so on and so forth. That's a transaction, and DNS works similarly in that we have a DNS client and a DNS server working together to make this magic happen. Now, a DNS client is the system that wants to resolve a domain to an IP. So think of this maybe as your workstation, and you're browsing to google.com, but you need to know the IP address of google.com to be able to do that. So that's the DNS client, and you're going to send your request to a DNS server. Now, the simplest way to think about a DNS server is really just a database server, because that's all a DNS server is. It's a database server that contains a listing of DNS to IP address mappings and is responsible for responding to requests for information about those mappings from its clients. So the client will request that, basically making a database query, and the DNS server will essentially respond to that information, and that makes up the DNS transaction process, which we'll look at here in a minute. Now, there's an interesting word here, and it says in this description that a DNS server is a system responsible for maintaining a database of DNS to IP address mappings for a zone. A zone. What is a zone? Well, that's DNS terminology for an area of the namespace that the DNS server is responsible for. So I own chrissanders.org, so there's a DNS server that is authoritative or responsible for the chrissanders.org zone. So everything underneath that. And I say underneath that because DNS exists as a hierarchy. And I'm talking about a global hierarchy displayed similarly to what we have on the screen here. So let's say I wanted to go to, in this case, Microsoft.com. Well, my DNS server, I have a local DNS server on my network, right? And it may be authoritative for chrissanders.org, but it's not authoritative for Microsoft.com. It doesn't know what those mappings are. There's only, the only systems that do are the ones that belong to Microsoft. So we have to be able to communicate with that system. Now, the client isn't going to go communicate with that system itself. The server is going to do that for it. And that's done via a process called recursion. So if the client asks the server a question it can't answer, that server, assuming this is allowed in its configuration, will recursively go out and find the answer by traversing the hierarchy you see on the screen here. There's a root domain and root servers that it's going to know how to communicate with, and we have those all the way at the top level domain level. So we have .edu, .com, .gov, .org, etc. So it's going to go traverse this hierarchy through, the root level domain, then .com, then Microsoft.com, and that'll get it to the Microsoft.com authoritative server, so it can finally get the IP address from Microsoft.com. Now, if it's going to a subdomain, it might have to go even one step lower. We see here sales.microsoft.com. And then, of course, we see one additional level for computer1.sales.microsoft.com. That's where we have the distinction of internal non-accessible DNS versus accessible DNS. We don't necessarily want someone from the outside to be able to find out what the IP address of computer1.sales.microsoft.com is. That's not good information for someone else to have. And also, it's probably going to be a non-routable IP address, right? It's going to be one that's not publicly accessible anyway. So there's a little bit of security architecting that goes on between how DNS servers are configured and what those servers are, what kind of requests those servers are allowed to respond to, and how you divide up those zones. But you can kind of see this concept of this DNS hierarchy that goes all the way from root domains and root servers down to top level domains, second level domains, further subdomains, and so on. And that's what the server is responsible for traversing to find an answer. Ideally, if your DNS server is configured correctly, if the answer is out there, it should be able to find it for you via this recursion process. And we'll look at a couple examples as we move forward. One of a very simple direct query from a client to a server that knows the answer, and the process of recursion and what that looks like both on the client side and on the server side. Now we're looking at the DNS packet structure. And again, we're not going to focus as much on structure here, more function, which we'll get into in just a second. But I do want to show you a couple of things here. Notice we have some specific terminology being used, questions and answers. So we see question count and answer count. That's the normal, that's basically the DNS term for query and response. So with other protocols, I talk about query and response and may still use that interchangeably here. But in DNS terminology, we're asking questions and getting answers from our DNS server in this case. Now this structure, this packet can be a lot bigger than it looks. So we have the concept of a question count and answer count. So you can have multiple queries within a single packet, right? Multiple questions being asked. So I can ask for resolution information for multiple domains. And furthermore, the server can respond with multiple answers for a single question. So a single domain may resolve to 5 different addresses. And that's perfectly okay per how DNS and the internet works. So the number of questions and answers will be specified here so that the receiving system knows how to process the packet and how many questions and answers to look for. And the appropriate questions and answers themselves will be in the 4th row here, the question section and answers section, which is where we'll see that data. So we'll look at some packets here in a minute, and this will make a lot more sense. But I do just want to drill into the fact that when we talk about DNS transactions, just so you're aware of the terminology, we have a DNS client, a DNS server. The DNS client asks a question of the server, and the server provides an answer back. This is the only thing the client will generally ever see. There may be a recursion process going on upstream from the DNS server, which we'll look at in a stimulus and response example later. But from the client perspective, this is what we'll see, and question and answer is the appropriate terminology. As I said, many people still call this query and response. I still do that myself. You may hear me interchange those a little bit. But if you're having to troubleshoot DNS, doing some Googling, you may have to search specifically for things related to questions and answers versus query and response to get the answer back you're looking for. One last thing before we start looking at stimulus and response and looking at some packets. So far, I've only mentioned the example of resolving a DNS name to an IP address, specifically an IPv4 address. But there are actually quite a few other things DNS can be used to resolve as well. And it does this via these query types or question types. So here I have the value on the left, but the type column in the middle is the most important. That's what we generally refer to when we talk about DNS query types. And the most common is what we call an A record, and an A record is simply an IPv4 to hostname to IPv4 mapping. And notice this is specifically IPv4 in this case. We have a couple other things that are of interest as well. We'll look at some of these, but not all of them. For instance, we have an NS type, which is a query for an authoritative name server for a zone. We'll see that. You see that when recursion's happening. We have MX, mail exchange, which is how a device will figure out how it should be sending email or who it should be sending it to. We also have AAAA, quad A. That's for IPv6 host addresses, so mapping a DNS name to an IPv6 address. So whereas DHCP couldn't really be retrofitted easily and you had to create DHCP v6, DNS works just fine for IPv6 records. So there's no such thing as, in this case, DNS v6. We can just use normal DNS and use AAAA records to get the information we need. Lastly, we have the concept of zone transfers. We'll talk about those here in a minute, but zone transfers basically allow one DNS server to transfer all of its records or part of them to another server, either full or incremental zone transfers. So those are instances where we might see DNS occur over TCP, whereas it regularly occurs over UDP otherwise, minus a few other specific scenarios. But these are the more common question and answer types you'll see. We'll dig into a few of these next as we get into stimulus and response.